started. Our next thesis is from Owen. I've really enjoyed talking to Owen about his thesis. It's right up my alley, genetics and viruses and bacteria and antibiotics, all those things I love to talk about. So had a great time talking to Owen about it. These are his words. He says, "First, I thank God for the strength and patience to actually get the thesis done. To my family, thank you for all the support, encouragement, and food so that I don't pass out in the middle of finishing my thesis. To my advisor, Ms. Bea, I'm grateful for the support and freedom you gave me in finishing the thesis. And lastly, I would like to thank the bacteria for being so hard to kill that I made an entire thesis for you guys." His title is The Last of Us, Why Viral Outbreaks Are the Solution for why viral outbreaks are the solution for the antibiotic crisis. Sorry, I've had trouble saying it. I'm going to set the timer up and you can start in a second. All right, you can start when ready.
Picture a pasture. Green, lush, shared by every farmer in the village. One farmer adds a second cow. Why not? There's plenty of grass, and another one does, and another. Nobody owns the pasture, so nobody cares to protect it. Each decision is rational, but each decision quietly kills the resource. Now, picture the pasture today. The grass is gone, the cows are still fat for now, and the farmers are bewildered, blaming at each other. In 1968, ecologist Garrett Hardin called this the tragedy of the commons. Today, the grass is antibiotic effectiveness. 80 years of individually rational prescriptions, 80 years of individually rational corporate withdrawals, and 80 years of individually rational decisions, and somehow, the most important modern medicine is nearly gone. The market did not fail because the wrong people were in charge, but it failed because antibiotics are designed to lose value the more they are used. Today, I will argue that we must adopt bacteriophage therapy not as a replacement, but as a complementary alternative to antibiotics, because it is the only solution that is biologically, structurally, and economically aligned with the problem. Let me show you how we got here. In 1928, Alexander Fleming discovered penicillin. This ushered in the golden age of antibiotics. Between 1940 and 1960, scientists discovered more than 20 new classes of antibiotics: tetracyclines, cephalosporins, carbapenems, and for the first time in human history, bacterial infection was not a death sentence. But the 1990s, antibiotics were overprescribed, misused, taken improperly, just because they were easy. And bacteria, being bacteria, evolved. MRSA rendered the entire beta-lactam class, the most extensive class in antibiotic history, obsolete. Then tuberculosis, then gram-negatives, then the nightmare. In 2016, scientists discovered the first pan-drug-resistant bacteria, CRE, a bacteria that is resistant to every single antibiotic we have. And that was not it. Shortly after, 2 more antimicrobacteria classes turned pan-drug resistant. For the first time in human history, bacteria is back to become untreatable. By 2019, antimicrobial resistance is responsible for more than 4.7 million deaths annually. The WHO classifies it as one of the top 10 global health threats, and yet we have not found a single new class of antibiotics since 1987. So, why can't we make better antibiotics? The core problem is the red-green hypothesis. Van Valen proposed that any co-evolving system, an organism must adapt just to survive. He borrowed this metaphor from Lewis Carroll's Through the Looking Glass. It takes all the running you can do to keep in the same place. Well, antibiotics don't run. Once created, their chemical structure is fixed. permanent, immutable. And bacteria? A single bacterium can divide every single 20 minutes. Within hours, their population can reach trillions, and under antibiotic pressure, the resistant one survives, and they replicate. It used to take bacteria decades to overcome an antibiotic. Now, it takes mere months. And the pharmaceuticals industry's response? Chemical diversification, creating derivatives of existing class products. But it's like rearranging the molecular furniture while the entire evolutionary house burns down. Consider teixobactin. Hailed as one of the most promising antibiotics since the 1980s, it targets a building block so essential that resistance is almost impossible. But teixobactin is still a fixed chemical. It cannot adapt, it cannot evolve, it cannot replicate at the site of infection. This is the mismatch of the problem. We are fighting an evolving enemy with a static weapon. Bacteriophages are obviously different. Phages are viruses that infect bacteria. They attach to the bacterial cell wall, inject their DNA, hijack the cell, and replicate until the host cell bursts. But most importantly, phages evolve with the bacteria they target. When bacteria develop CRISPR-Cas defenses, phages just develop anti-CRISPR genes. When bacteria modify their cell wall, phages just create new bacterial surface receptors. This back and forth has been happening for 3 billion years. Phages don't stand still. They run. We also have real-world proof. In 2016, a patient from UC San Diego was dying from a pan-resistant Acinetobacter baumannii, one of the 3 families that is resistant to every single antibiotic we have. He then received an intravenous phage cocktail, and he recovered. Unlike antibiotics, phages are precise. Broad-spectrum antibiotics destroy entire microbiomes, the trillions that protect your gut, train your immune system, digest your food. Broad-spectrum antibiotics destroy all these. And opportunistic infections fill the vacuum. The most notorious C. difficile kills tens of thousands annually, not because of direct exposure, but antibiotics created the space it needed to grow. Phages do not do this. They are so specific that they can kill the bacteria without even touching the surrounding microbiome. Biologically, the case is clear. Antibiotics treat bacteria like they are static objects. They aren't. Phages treat bacteria like evolving organisms because they are. But the failure of antibiotics is not only biological, it is structural. Consider what modern medicine actually relies on. Organ transplantation requires suppressing immune system. Cancer chemotherapy destroys immune function. Cardiac procedures, intensive care, joint replacement, all of these procedures rely on the assumption that infections can be controlled. And none can afford for that assumption to fail. And yet, as resistance is rising, that assumption is collapsing. Hospitals are already closing operating rooms because of viral infections. Surgeons are delaying procedures. Transplant programs are tightening eligibility. This is not the future. This is happening now. And the pharmaceuticals industry's response? Between 2003 and 2013, Novartis, AstraZeneca, Sanofi, and Allergen all exited antibiotic research. Not because they lacked the science, but the economics made it impossible. The failure is massive. Today, it takes more than $1 billion and decades of research just to develop one single antibiotic. And we are also asking these same people not to use those antibiotics because of stewardship. Essentially, developing an antibiotic is economically suicidal. Acogen created plasmamycin, a drug approved by the FDA in 2018 for multi-drug-resistant infections. The drug was clinically effective and was urgently needed. Yet, it only generated $1.2 million in revenue compared to the $1 billion it needed to create the antibiotic. The next year, the company filed for bankruptcy. The drug was needed, but the company died anyway. Now, does phage therapy solve this problem? Look at Belgium. Under Belgium's magistral framework, a hospital maintains a phage bank of pre-certified phages. When a patient is admitted for a resistant infections, a physician just prescribes a personalized cocktail of phages. Then, the pharmacist creates the cocktail on spot, just like how any pharmacy creates personalized medicine. No billion-dollar clinical trial, no decade-long approval process, just an evolving, adaptable treatment prepared and administered within the healthcare system. The Eleva Institute has existed for a century. The FDA expanded access has already saved lives. The infrastructure exists. The precedent exists. The question is whether we choose to build it. But let me now show you why the antibiotic market can never fix itself. Most drugs maintain a stable value. A diabetic medication works identically, prescribed to one patient or a million. Efficacy is constant and revenue is predictable. Antibiotics? Every single prescription creates selective pressure for resistance, which makes the drug progressively worse for everybody simultaneously. The more successful antibiotic, the faster it becomes obsolete. In essence, success accelerates obsolescence. This is the tragedy of commons applied to medicine. Every prescription is rational, but collectively, it exhausts a resource. And no amount of market optimization can solve this. Consolidations, price adjustments, patent extensions, none resolve the fundamental issue. Antibiotics are designed to lose value the more they are used. This is what economists call a Keynesian market failure. In the Great Depression, individuals saved money, which was rational. But when everybody saved simultaneously, consumer spending collapsed and the market imploded. The same logic applies. When a company leaves antibiotic research, it is rational. But when every single company exits research simultaneously, this is catastrophic. Phages invert this entirely. First, discovery is cheap. Phages exist wherever bacteria exist, in sewers, in sewage, in oceans, and characterizing a single phage costs around $10,000 to $100,000 compared to the $1 billion needed to develop an antibiotic. Second, phages benefit from network effects. Metcalfe's law states that in any network effects, Metcalfe's law states that a network's value grows proportionally to the square of its connected nodes. In essence, a library of 100 phages creates 4,950 possible combinations. A library of 1,000 phages creates nearly 500,000 of combinations. Each new phage doesn't replace the other one. It multiplies the possibilities. Third, and lastly, phages are capable of biological updating. When bacteria grows resistant to phages, the natural selection in the phage population counters it. This makes phages therapeutically relevant with minimal human reinvestment. And the economics is also proven. Belgium's magistral system costs around $500,000 to establish and around $250,000 to maintain annually, comparable to a standard diagnostic laboratory. The O'Neill Review estimates that unchecked resistance will cost us 10 million lives annually and cost the global economy $100 trillion. If these phage libraries just address 10% of these carbapenem-resistant infections, how many lives can we save and how many trillions of dollars can be saved? But all is not over for antibiotics. There is also a legislative pathway. The PASTEUR Act, currently before the US Congress, proposes a subscription model. The government pays a fixed annual fee for access to antibiotic, regardless of how many doses are sold. Like Netflix, you pay for the library, not for the episode. This eliminates the tragedy of commons entirely. A company no longer loses revenue because of stewardship programs. The more successful antibiotic, the more it becomes protected, and the more the developer is compensated. This is not a scientifically complex topic. It is only a decision that has not yet been made. I anticipate three objections. First, won't bacteria just develop resistance to phages, just like how they did to antibiotics? Yes, this objection first is valid. And yes, bacteria will grow resistant to phages, but it misunderstands the fundamental difference. Antibiotics are chemically frozen. When a bacteria grows resistance to it, it cannot adapt. Phages are evolving. When bacteria grows resistant to phages, the natural selection in the phage population counters it. Second, phages are too specific. In an emergency, there is no time to match a phage with a pathogen. Again, this objection is correct, but it misunderstands how phage therapy is deployed. Pre-designed phage cocktails already target the most common resistant infections. It can also provide broad-spectrum coverage comparable to antibiotic, and it can also be quickly administered from a phage bank. Furthermore, nobody proposes that we must adopt bacteriophage therapy as a replacement for antibiotics. The current standard that's being adopted is PAS, phage antibiotic synergy. Antibiotics provide broad immediate coverage, while phages provide follow-up to eliminate the remaining pathogens. These two are complementary, not competitive. Third, phages can never be patented. Without market exclusivity, no company will ever fund development. I will argue that this is exactly the point. The patent-driven pharmaceutical model for antibiotics have failed. We have established that companies that made new antibiotics went bankrupt. The system cannot provide what society needs because antibiotics are designed to lose value the more they are used. Without patents, competition shifts from market exclusivity to service quality, precision matching, rapid sequencing, manufacturing capacity. The cost to entry drops from $1 billion to around $100,000. A phage library grows through contribution. As more hospitals characterize more phages and add them to shared banks, a library's value compounds exponentially. A global pharmaceutical model cannot replicate this because phages are not pharmaceutical products. They are public health infrastructure. The farmer in Hardin's pasture did not stop adding more cows because they were greedy. They stopped because the grass was already gone. We have spent 80 years rationally prescribing, rationally withdrawing, and rationally watching the fields go barren. Bacteria did not beat us with malice, but with mathematics. But, unlike Hardin's farmers, we can still see the grass. The answer did not begin in a laboratory or a billion-dollar clinical trial. It began 3 billion years ago in sewage, in oceans, older than the crisis, older than medicine, even older than humanity itself. The Belgian Medusa system exists. The Eleva Institute has operated for a century. The FDA expanded access already saved lives. The PASTEUR Act is currently before Congress. The obstacle is not science, not infrastructure, but a decision. We do not need to invent the solution. We only need to choose it. before the last blade of grass is gone. Thank you.
Thank you. Good job, Owen. Our panelists today are Mr. Felix and Mr. Hans. I'm going to let Mr. Hans go first.
Test. All right. Good morning, Owen. Feeling
Morning, sir.
better? Not parched anymore? Okay, and of course. And of course, you would wonder what a physics teacher is doing here, but then hey, more opportunities to learn new things, am I right? Just a quick comment though. I take it you take the title from the game. You do know what causes the zombie outbreak in the game,
Yes.
correct? And last time I checked, it's not viral outbreaks.
Technically, yeah.
It's a fungi.
Yes.
Cordyceps. Okay. Besides the point. But I would like to give a few compliments for the thesis. It is genuinely an enjoyable read. I learned a whole lot. I've only heard the topic once in a while about the existence of superbugs. I think at one point it becomes like a topic for like an MUN. I was teaching the kids, and it is very eye-opening. And I think you've built a fantastic case with, I would say, 6 pages of works cited, and I think all of it is worth it. A few comment. I'm aware that I think this is a comment that you've heard a whole lot, that it's very jargony, because it is a very detailed topic with a whole lot of, I would say, funky words. I do understand that. But regardless, you've made it clear all in your thesis. Just a little bit of comment on your speech. I do understand that the speech must be limited to 20 minutes, but I think you can do a better, trimming on your speech from thesis to speech, because maybe from the perspective of a person who has read the topic, I do understand where you're coming from. But maybe for those who might not be as knowledgeable, who might not be as informed through the thesis, it might be a bit confusing. And sometimes with the pronunciation of the difficult substances, I'm aware it is a bit difficult, but then I think you can improve on that part. So a few comments, but overall, great thesis, enjoyable read, and it's very informative and persuasive. Now for the questions. I would say these are the questions that you might not have addressed in your refutation. My first thought on reading this concept is it is a system of coevolution in which it's basically an arms race, right? Who gets to out-evolve the other. A quick question that I would have from me is, is there a case that such a treatment having a phage gone rogue, like they over-evolve, they did defeat the bacteria, but they end up producing, I would say, an unwanted side effect of the evolution that's attacking other parts of the microbiome due to that evolution? Because in general, natural selection does happen on a random basis, right? We'll see who survives, and then the one who survives gets to pass down the genes. Has there ever been a case where these phages gone rogue, and what happens if it does? That's my first question.
Thank you for the question. As far as I have researched with the limited amount of clinical information we have for phage therapy, there is no gone rogue phage therapy treatments. But there may be a few cases where phages become rogue. Mainly, they kill bacteria faster than the antibiotic can treat them, and like phage antibiotic synergy. So both of them have to work together. But when phages are too effective, the antibiotics cannot work properly. Yes.
All right. Thank you for the response, because it feels like you actually have made a case there. Okay, even if it evolves, it won't over-evolve to the point that it will destroy the other microbiomes, right? But then I also have, I would say, a part of curiosity of mine in which instead of over-evolving, what if the bacteria wins the arms race? So the phages not being able to catch up with the evolution of the bacteria, thus the phages simply got outnumbered, or they even got killed by, well, maybe their phages, their viruses. They technically can die, but then at the very least, their genetic material is actually destroyed, overempowered by the bacteria they're supposed to kill. Has there ever been a case? And if that's the case, what has happened?
Yeah, so actually, a bit of lore is that the 2016 USCD case, the first phage that was applied was actually grown resistant by the bacteria. That is why they had to went to the lab and scrum, and they had to like find a new phage even stronger than before. But if phage actually dies, then we have another solution called phage antibiotic synergy. Antibiotics first weaken the cell wall, and then the phages go inside and finish the job. So technically, we need to use both together.
Right. Thank you for the answer. And now some of these, I think it's just more to my personal curiosity, because I would say that my favorite isn't necessarily biochemistry. There's that. Maybe you'll find a whole lot more detailed questions with Mr. Felix later. Um, but I would like to ask, I would say just this one. I do have my note here. I do believe, network effects. You did say that this network effect contributes to the nonlinear growth of the phage library, but I would like to know a bit better. Especially, you did mention about Metcalfe's law. Can you elaborate a bit more as to how does that, I would say, manifest in terms of its bioeffectivity? Like, how effective is it, or what does it exactly contribute for this phage therapy?
So, for some bacteria, it would be necessary to provide more than one phages. That's why there's something called a phage cocktail. But sometimes also we do not have enough time to characterize the phages. That's why the Belgian magical system exists. We like cook a few phages up together and call it a cocktail, and we inject it. So technically, Metcalfe's law is a way I can show that the amount of possibilities of these cocktails. So it's not a sense like on how many things it can treat, but on how much probability that it can kill the bacteria.
Okay. So the argument is like, with this amount of phages in the library, the combination is bountiful to the point that with this access, like you did akin it to Netflix, like with this amount of access, it can treat, the possibility of treatment is a whole lot bigger, and it grows non-linearly, right? Okay. Thank you for the clarification. Now, I would say the second part that I'm curious about is the process of bioprospecting. You did say that, you take bacteria wherever they exist, right? In the ocean, in the sewers. Maybe listening to that is not necessarily the most convincing, especially if it's from the sewers. But then, of course, bacteria exist everywhere, even in the current air that we're breathing, right? What process exactly happens in that bioprospecting process?
Ooh, as far as I know, so we can't just take phages and inject them to the human body because that's bad. So the first thing we must do is to separate something called a lytic phages and lysogenic phages. Basically, we want these phages to kill the bacteria because some of them actually inject their DNA and just sit there. So we must separate it to lytic phages. Now, the second thing we must do is to clean it. This can be done through ultrachromatography, which cleans out the endotoxins. And then we also have to test the effectivity of it by taking a sample of the phages and putting in a petri dish and putting the bacteria with it. If the phages kill the bacteria, then if it is effective, then we can inject it to the human body. Yes.
Right. Thank you for the enlightenment. Just making sure. How many more minutes do I have?
Got, well, technically 30 seconds, but if you have another question, you can go ahead.
I would say, well, in that case, I think I'll just edit there. I do have a whole lot more questions because, once again, this is a very novel topic for me. But regardless, thank you so much for your answers, and it has been absolutely informative and enlightening. So once again, thank you, Owen.
All right, Felix.
Hi, Owen.
Hi, Mr.
Um, I really, really love your topic, by the way. I really love your reading your paper. It brings out the nerd in me, so thank you. Yeah, and yeah, really just there's moments when I read your paper and I'm just like, wow, this is so cool. So well done there. Yeah. So. My first question is related to just phages itself. So you said that it's injected. Is there any other method of administration for for phages?
So there's actually a product in a market already called Pyophage, which is already created by the Elevia Institute in Georgia that has existed for a century. This Pyophage can be used in many ways. It can be nebulized to inhale for lung disease. It can be applied for skin wounds, but it can also be ingested, but you have to drink antacid so that the acid doesn't kill it. Or you can also inject it to the human body.
Okay, so do you think this phage therapy can be used for any bacterial infection? Let's say somebody has a staph infection or somebody has a strep infection. Like, does it work for every single type of infection, bacterial infection there is?
Yes?
Okay. Um, Now, more on the big pharma side of things. You said that big pharmas are now exiting the antibiotic research. Um, yeah, they're now exiting antibiotic research. So should then we completely switch to phage therapy instead of using it as a complement? What do you think?
No, because like it will make a dependency on phages, right? So if phages for some reason fail, then we literally have no other option. So I think it is a better idea if we invest on both. So if one fails, then we have another one to back it up, although it is expensive.
So what do you say to the big pharmaceutical companies who are actually exiting the antibiotic research?
I don't know, it is technically rational, but you guys should support the Pasteur Act, which is currently before Congress, so that you guys don't lose that much money developing an antibiotic.
Okay. Now let's compare some of the recent research on antibiotics and also phages and see if phages is actually a good complementary. So have you heard of self-destructible antibiotics?
No.
Okay. So these are antibiotics that are programmed to deactivate after clinical utility is achieved. So once all the bacteria are killed, then it deactivates itself, therefore it prevents resistance. So what do you say with this new technology with antibiotics? How do you compare that to your phage therapy? What do you think?
That is a very good alternative, but again, it creates a dependency if we rely on that. I mean, it is very, very futuristic, like how I said with Teixobactin, right? It's very, very future, but at one point, the bacteria will obviously go resistant to it. So technically, even if it is a good solution, we must still invest in phages because we have two solutions that can complement each other.
Okay. So that may be something that it's a new technology. So that might be something for the future. Now, maybe for something that has already existed, which is called prodrugs. Do you know what they are? Prodrugs.
Prodrugs.
Have you heard of that before?
No.
Okay, that's fine. So prodrugs are they're chemicals. They are not activated until the bacteria interacts with it, right? So usually we can change the antibiotic molecule to its inactive stage. Once it's in the person's body, it's going to react. The bacteria is going to interact with it, and then it's going to enter the bacteria and it's going to kill it from inside out, which is why we also call it the Trojan horse delivery. So yeah, I'm glad you think it's cool. I think it's cool too. So what do you think about this new technology? Like, it's already existed. People have been using this. So why do you think it's, like this phage therapy? Does it add on to anything, or should we just keep researching on prodrugs and then use this method? What do you think?
I think, like, again, back to my point, is that we should not make a dependency. Although these drugs, these prodrugs, this Trojan horse like zorusubalpin is effective, but we are still making some sort of a dependency. again, like the main problem is the red queen hypothesis. Like they are not evolving in any way, and if bacteria grows resistance, we must research again and again, another 1 billion and another 1 billion. But phages are more like evolving. It's not that high of a cost, so I think we must use it as a complementary alternative.
Okay. Now, for phages, let's talk about phages, right? I like that you mentioned that phages are specific, right? And so, at what point do phages become way too specific? Like we know that broad spectrum antibiotics are able to kill multitudes of bacteria. You mentioned that yourself. But at what point do phages become way too specific for us to be able to, like, will it eventually come to a point where it can't kill the bacteria that it needs to because it's way too specific? What do you think?
Technically, it's already way too specific. Phages can only target one single bacteria and not one single species, not even in the same family. That is why we have cocktail of phage, cocktail of phages. We mix different phages together so that we hope that it might target this bacterium family.
Okay. With the just continuing from what Mr. Hans asked you, right? He asked you about the side effects of phages, right? And then, in addition to that, you mentioned the way that we do this is by phage training.
Yes.
Is it possible to create a super phage that may have unforeseen consequences on the human body? We're talking about potential here, potential risks.
Like potential as in attacking the human body?
Yes.
No.
And why not?
So the mechanism of action of a eukaryote and a prokaryote is different. So bacteria has a cell wall, but human cells have a plasma membrane. The second thing is that in the bacteria, the DNA just floats around, while in the human cell, the DNA is already in the nucleus. So when phages enter the bacterial cell, the DNA gets inside. And because the bacterial DNA is already outside, the RNA can just decode it anytime. But in the human cell, when the DNA is already inside the nucleus, so when you try to inject another phage DNA on it, technically it won't work because nothing will meet it. Yes.
You mentioned, I mean, follow up to that, right? You also mentioned that these phages can, by natural selection, adapt, right? Even though they're not living things, right? So would it be able to adapt in the human body to the point where it can attack our eukaryotic cells?
No, because so phages target bacteria, but if you want to target human cells, you gotta like move up the steps of the evolutionary ladder. You know, like you can't just go from bacteria to directly to human cells because the jump is way too far. Thank you.
Okay. Yeah, this is so cool. Okay. Yeah. So you also mentioned, I really love this part also where you said that phages are self-limiting, right? So it can stop itself, right? Before, yeah. So I'm thinking about chronic infections, right? So things like multiple sclerosis and things like that, where the bacteria can actually become latent. You know what latent bacteria is, right? So it's undetected. It's at a level where it's not dangerous at that point, so it's undetected, but once it multiplies, it can cause more infection, even worse, right? So this is what we call latent bacteria. Now, what happens if the phages actually deactivates before it can kill all the latent bacteria? Do you think it's still a viable option for chronic illnesses?
You mean like the phages don't inject their DNA, or like when they inject the DNA, it doesn't work?
Right. No, not it doesn't work. Like it stops working because it's self-limiting. Right? So once the bacteria becomes latent, so it's undetected, the phages would just stop working because it would just deactivate itself because it can't detect the bacteria anymore. Do you think there's a potential for that? And if so, what do you suggest?
Yes, there is a potential for that. I think technically I did not research enough until that point, but the best thing I can give you is that we can still use antibiotics because again, it's like a nuclear bomb. You're gonna use it as gambling. You gamble that it's gonna take out the latent bacteria as well, aside from the trillions of microbes that exist in your gut. Yes.
Okay. Another point of discussion. Biofilms, right? So bacteria have, you said bacteria have biofilms, right?
Yes.
And so that's one of the reasons why it can resist antibiotics, right? And like you said that the phages can bypass this?
Yes.
Yeah, okay, so yeah, so this is just another risk, yeah, thinking ahead. Do you think, so we have our mucosal membranes, right, in our human body, which quite has some similar characteristics to the biofilms, right? Do you think the phages will, again, adapt and evolve to the point where it will actually go through our mucosal membranes? What do you think?
Again, I did not research that far. Sorry, but I think I don't think there is. I mean, the phage could actually destroy the mucosal membrane, but again, it cannot attack the actual human cells. That's the best answer I can give you.
Yeah, it's okay. Thank you.
Time is actually up.
Okay, yeah,
So-
that's all I have anyway.
job,
Thank you so
Owen.
much. Well done.
All right, so we will meet, Owen will meet friends and family, panelist, advisor over here for photos, and then we will start again.